So as we learned in Chapter 7, quantum mechanical theory describes the behavior of electrons in atoms. The electrons exist within orbitals. And we looked at the shapes of those orbitals. If we want to identify where the electrons for a given atom are, what orbitals they are in, we call that an electron configuration. How are the electrons configured? What orbitals are they in? So for a hydrogen atom, there's only one electron, and that electron is going to be in the first principal quantum level in the only orbital that's there, the s orbital. And we refer to that as the 1s orbital. 1 is the principal quantum number. S is for L equals 0. It's a spherical orbital. And then as a superscript, we write the number of electrons that are in that particular sublevel. So this is a place where chemists do write the number 1. So if there's a 1, you need to write it. Other places, we leave them out. Calculations using Schrodinger's equation show that hydrogen's 1 electron occupies that lowest energy orbital. We can solve Schrodinger's equation for the hydrogen atom because there's only 1 electron. We can't solve that equation for multi-electron atoms, which is everything else, because the electrons interact with each other. And so that makes the math even more complicated. But we can get approximate solutions, and those show that the orbitals in other atoms are hydrogen-like. Okay. The two factors that affect multi-electron atoms are electron spin and the energy splitting of sublevels. We'll talk about those. So electron configurations tell us, a shorthand way of where are the electrons. A more visual method is called an orbital diagram. And so here, an orbital is represented as a box, and the electrons are represented as arrows. These arrows only have half of the arrowhead, just because. So we've talked a little bit about the spin of electrons. We said it could be positive or negative. We can think of it as spin up or spin down. So in an orbital diagram, we show the spin of the electron. An arrow pointing up is spin up, and an arrow pointing down is spin down. So if you have a group of hydrogen atoms, about half of them have electrons with positive spin and half with negative spin. Each of those atoms only has 1 electron. Pauli Exclusion Principle says no 2 electrons in an atom may have the same 4 quantum numbers. So if we have 2 electrons in the same orbital, say in the 1s orbital, they're going to have 3 of their quantum numbers identical. N equals 1, L equals 0, M sub L equals 0. The 4th quantum number, they must have different numbers. So 1 will be plus 1/2, 1 is minus 1/2. It's a little bit like a social security number or an address. You can't have 2 things with the same address when they're different things, right? You can't have 2 people with the same social security number, right? It's big problem. So each electron has its own set of 4 quantum numbers, okay? So what that means is that each orbital can hold a maximum of 2 electrons, and those 2 electrons must have opposite spins. Because if their spins were the same, then they would have the same 4 quantum numbers, and that's not possible. So we can figure out how many orbitals are in a sublevel, and knowing that there are 2 electrons max in each orbital, we can figure out how many electrons can be held in a sublevel. So an S sublevel has 1 orbital, so it can hold 2 electrons. The P sublevel has 3 orbitals, those 3 2-lobed things in perpendicular in 3-dimensional space. So it can hold 6 electrons. The D sublevel has 5 orbitals, it can hold 10 electrons. The F has 7 orbitals, it can hold 14 electrons. So if we look at helium, the next most complicated element, 2 electrons, right? Electrons are going to go into the lowest energy orbitals, and so for helium, its 2 electrons are going to be in that 1s orbital. The first principal energy level, there's only 1 orbital there. That orbital can hold 2 electrons, and so the 2 electrons are going to be in there. One's going to be spin up and one's going to be spin down. So that when we look at the quantum numbers for these 2 electrons, the first 3 are identical, but the last one's different. Each electron has its own unique set of 4 quantum numbers. Kind of like Mr. Bela was saying in that video with the address, right? You've got your name, you've got the street number, you've got the street name, you've got the city, right? So you can't have all 4 of those things be the same, because 2 people can live in the same house, but you can't live in the same house and have exactly the same name. It just doesn't happen, right? The sublevels in each principal energy level of hydrogen all have the same energy, and so the orbital energy only depends on the principal quantum number. When we have orbitals, different orbitals that have the same energy, we say they're degenerate. So they have the same energy. That's not the case in multi-electron atoms. The energies of the sublevels are split. They're not degenerate. And this is caused by charge interaction between the electrons, by shielding, and by penetration. So in general, the lower the value of L within a principal level, the lower the energy of the orbital. So SPDF, this corresponds to L being 0, 1, 2, and 3. So in a given principal energy level, the energy increases 0, 1, 2, 3, SPDF. In hydrogen, on that second level where there's 2 different sublevels, that they have the same energy. But that's not the case in any other atom. So Coulomb's law gives us the relationship of the potential energy of 2 charged particles with their charges and their separation. And I'm not going to ask you to do any calculations with Coulomb's law, but it's very helpful to have a basic understanding. So this is the part that we're interested in. This part is just a constant. So the energy, the potential energy of 2 charged particles is equal to this constant times Q1, Q2 over R. Or we can say the energy is proportional to Q1, Q2 divided by R. Q1 is the charge of one particle, Q2 is the charge of the other particle, R is the distance between them. So as the distance between them gets smaller, the potential energy gets greater. Energy can be positive or negative. Negative energy is stabilizing, positive energy is destabilizing. You're going to have a negative energy, an attraction between these when one of these is negative and one's positive. The bigger the charge, the stronger the attraction. The shorter the distance, the stronger the attraction. This is similar to how magnetic fields work, and so if you can imagine with me the refrigerator, and you have a piece of paper that you're going to stick on the refrigerator with a magnet, right? You stick it up there, all is good. Oh, I need to put another piece of paper up there, and now you're going to got 2 pieces of paper under the same magnet. And let's keep going. 3 pieces, 4 pieces. What's going to happen eventually? It's going to slide down, right? Because that piece of paper, even though it's very thin, is putting more distance between the magnet and the refrigerator. And at some point, it's no longer able to hold strong enough to keep the paper from sliding down the refrigerator. If you took that same number of pieces of paper and used a stronger magnet, it would hold, right? So the strength of the magnet is like this Q1, Q2 thing, and the distance is like R, okay? So Coulomb's law is going to help us understand a lot of things in this class. So when we're looking at the electrons in an atom, the electrons are attracted to the nucleus. The nucleus is positive, the electrons are negative, so there's an attraction there. But the electrons are repelled by the other electrons around them because negative and negative, like charges, repel each other. So what happens is that the presence of other electrons reduce the attraction that any one electron has for the nucleus. We say that the other electrons shield the nucleus. And so the total amount of attraction that the electron feels is less. It's called the effective nuclear charge, or capital Z F for effective. Come on. Yeah, we'll get to a picture in just a minute. Penetration is the idea that the closer the electron gets to the nucleus, the more it's attracted to it, right? That's that 1 over R relationship. So if the electron is closer to the nucleus, it's going to be more attracted. So the better an outer electron is at penetrating the electron cloud of the inner electrons, the more attraction it will have for the nucleus. And how much those orbitals penetrate in close to the nucleus depends on the orbital's radial distribution function, the shape of the orbital. So here we have an illustration of a lithium atom. So here's our nucleus with a positive 3 charge, and lithium has 3 electrons. And so we have these 2 electrons that are going to be in that first energy level in a 1s orbital. And so these guys are just, in there. This third electron is in the second energy level. It's further out, and as it looks at the nucleus, its attraction to the nucleus is reduced by the presence of these 2 electrons in there. These electrons sort of get in the way. They mess up the attraction that this electron has for the nucleus. Does that make sense? You can also think of it in a very simplistic way that, okay, there's a +3 charge on the nucleus, and then there's these 2 electrons that are in the way, and so my net effective nuclear charge is just +1 for that nucleus. It's a little more complicated than that, but that's good enough for our purposes. So this electron is only experiencing an attraction of about +1. So that's the idea of shielding. The idea of penetration is that if the orbital that this electron is in has some part of it that's in closer to the nucleus that penetrates into this 1s orbital where those other electrons are, now it's going to experience that full +3 charge because these electrons aren't getting in the way. Does that make sense? So if we look at those total radial probability distributions, here's the probability, and here's the distance from the nucleus. So the 1s orbital is off the chart here. A lot of density, very close to the nucleus. And here's the 2s orbital. It's got this lobe that's right here inside the 1s orbital. Most of its density is outside, but there's some that's inside. And then we also have the 2p orbital, and some of it goes into the 1s orbital's space, right? But what we see is that the 2s orbital penetrates more deeply into the 1s orbital than a 2p orbital does. So an electron in the 2p orbital is not going to have as much attraction as the 2s orbital. So electrons in the 2s orbital are lower in energy than in the 2p orbital. That's the energy splitting of those levels. is because they have different shapes, because they overlap differently with the other levels. So a 2s orbital has a space in here where the electrons can be very close to the nucleus, where they do not experience as much shielding. Now the ones out, the part that's out here does experience shielding, but the 2s will have a lower energy than the 2p. Any questions about that? Yeah.
So the electrons are orbiting every time, right? Is that what you're saying? And then they're getting closer to the nucleus, or they're just bouncing around?
Yeah, so that's hard to get our minds around, right? It's convenient to think about the electron as a particle going around the nucleus. That's friendly and nice, and we can understand that. But that's not what they're doing. So the electron is like a standing wave around the nucleus. And it's got a really weird shape, but this 2s orbital is a standing wave with part of it right inside here, and then there's a node, and a lot of it is out here. But the electron really is filling that whole region at the same time. Okay? But because it's got this area or volume inside the 1s orbital, it's going to be lower in energy than the 2p orbital, which has less that's very close to the nucleus. Does that help? So because of the penetration of the s orbital is more effective at penetrating than the p orbital, the sublevels in each principal level are not degenerate. They're not the same energy. In the fourth and the fifth principal levels, effects of penetration become even more important. And so then we actually get the 4s orbital being lower in energy than the 3d orbitals. And all has to do with the shapes of the orbitals and the penetration, how close they can get to the nucleus. The separations between sets of orbitals becomes smaller and smaller as you get past the 4s. And even more problematic is the relative energy ordering can actually vary among the elements. Thankfully, we don't have to worry about that. We can just pretend they're all the same. So this is how it works out for most atoms. So we're looking at increasing energy as we go up. So the lowest level, the lowest energy orbital is the 1s. The 2s is the next, and then the 2p. The 2p is a little higher in energy because it can't penetrate, it can't get as close to the nucleus as the 2s. Then we have the 3s, and then the 3p, and then the 4s, because of its ability to penetrate in, is actually lower in energy than the 3d orbitals. So it goes 4s, and then 3d, and 4p, and 5s, and 4d, and it's all kind of confusing at that point. I'm going to show you how we can just read that off the periodic table, and so we don't have to memorize that. We think about putting the electrons into the orbitals, filling the orbitals, and there's the Aufbau Principle. So electrons are going to occupy orbitals to minimize the energy of the atom. So they're going to fill the lower energy orbitals first before they fill the higher ones. Orbitals in the same sublevel, like in the p sublevel, there's 3 different orbitals. Those all have the same energy as each other. But the 2s and the 2p have different. Orbitals can hold no more than 2 electrons each. And the Pauli Exclusion principle says that the spins have to be opposite so that they have different quantum numbers. And then Hund's rule says that when we're filling those degenerate orbitals, we're going to fill the orbitals singly, put 1 electron in each orbital until you've got them all half filled, and then you pair them up with parallel spins. With opposite, yeah. They fill with parallel spins, and then when they pair up, they have opposite spins. Okay, so that can be a lot to try to take in, and it's very abstract. And so I've come up with this crazy analogy I call the Quantum Hotel, a discount resort for electrons in Mrs. K's chemistry land. Okay, so the first floor is like the principal energy level 1, right? The second floor is n equals 2, the third is n equals 3, etc. On the first floor, we have one room. So the room is like the subshell. That room is an s orbital, or the s sublevel. On the second floor, we've got two rooms, s and p, the s sublevel and the p sublevel. The third floor has 3 rooms, the fourth floor has 4 rooms, etc. Now, these rooms have different numbers of beds. It's a very strange hotel. The S room has 1 bed. That's pretty normal. The P rooms all have 3 beds, and the beds are the orbitals in quantum mechanics. The D rooms have 5 beds, the F rooms have 7 beds. I mean, nobody's seen a hotel that has 7 beds in one room, right? That's weird. You can only put 2 people in a bed, right? So the people are like the electrons. And so when you put the people in this hotel, you can't have more than 2 people sleeping in a bed. You could have 1. There can be empty beds. And then the opposite spins. So I kind of gave you a preview of this. So if this is a... No, that's not working out very well. I'm trying to draw a bed. And my mistake here is I'm trying to make it 3-dimensional. It's a fancy headboard, right? Oh. It's got to have some thickness to it. Okay, there's a bed. So person comes in to sleep in the bed, right? Or climb in, stick their head up here by the headboard, and they're going to lay down, right? The second person comes in to share this bed. So I imagine these as, really macho guys, right? Guys don't like to share beds with each other. Everybody okay with that, right? Girls, women tend to be more okay with that. It's like, I'll just sleep on my own side of the bed. It's fine. I want to be comfortable. My experience in college when we went on trips and stuff was that when the guys had a hotel room where there were 4 guys and 2 beds, 2 of the guys slept on the floor, right? Because they were not going to share. Okay, so in this hotel, the floor is lava. You can't sleep on the floor, okay? So this next guy has to sleep in this bed with a guy he doesn't even know. It's a very, very uncomfortable situation. So what he's going to do is he's going to sleep upside down. Yeah, okay. So where I'm going with this is that each of those boxes in an orbital diagram is an orbital. And we represent the electrons as arrows. The first one goes in, spin up. The second one comes in with opposite spin. To me, that looks like 2 people in a bed. Okay? Any questions so far? So now we can look at this diagram showing general energy ordering, and we can imagine that these are floors in the hotel. So this is the first floor. Here's the second floor. Here's the third floor, the fourth floor, the fifth floor. Now, the reason that the 2P here is shown a little higher is because that room costs more money to stay in, right? This is a discount resort, and so the electrons coming in here are trying to save money, and that's their primary concern. So as electrons come to stay in this hotel, the first one's going to stay in the cheapest room, which is that 1S room, and he's going to sleep right side up in the bed. Second electron coming in, very, very cheap, I'll take that other place, I'll sleep upside down in this bed. Next electron coming in has to go to the second floor, going to take the cheapest room. There's one bed in there, sleeps right side up in the bed. The next electron's going to choose that room also, share the bed, but not very comfortable about it. Next electron comes in. The two cheapest rooms are taken, so he's got to take the next available one, which is the 2P room. There's 3 beds in there. So he's tired. He's probably just going to crash in the bed that's closest to the door, because I imagine this is the hallway, and there's a door, and he comes in and he just crashes. Now, the next electron that comes in, he's coming into this room, and there's a bed with a guy he doesn't know sleeping in it, and then there's 2 empty beds. Is he going to snuggle up with this guy? No way. He's going to take his own bed, right? And that's the Hund's rule, that they're going to occupy separate orbitals with parallel spins. He's not going to choose to sleep upside down. He doesn't need to, right? What's the next electron going to do? Take that other bed, right? He's going to go in here. Another electron coming in, again, going for cheapest accommodations. I got to share upside down here. And then upside down here, and upside down here. So, are you getting the idea? Then they'll fill up this one. They'll go up here. And they're going to fill those separately first, and then pair up when they have to. Okay? Any questions? Yes?
Their spins have to be opposite of each other?
Yes. Because, we think about it, it's like, well, how can 2 negatively charged electrons even coexist in the same orbital? It's because their spins pair. And we don't need to understand exactly how that works. We can just say, oh, okay, there's an explanation. Their spins pair. Not sure exactly how that works, but it's okay. Yeah. So I will be referring to the quantum hotel a lot when I talk about making electron configurations and orbital diagrams and stuff. So just some general notes about electron configurations. Unless it specifically says otherwise, anytime you're asked to write an electron configuration, we expect you to write a ground state, where all the electrons are in the lowest energy states. We've learned that if you zap like hydrogen gas with electricity, you can cause electrons to go into higher orbitals. It's unstable. They'll come back down, and when they do, they'll release electromagnetic radiation. And some of those transitions give visible light. It's important to remember that the number of electrons in a neutral atom equals its atomic number. The atomic number is the number of protons, and in order for it to be neutral, the number of electrons has to be the same. The parallel spin of the electrons in the different half-filled orbitals minimizes their mutual repulsion, and then each orbital can hold a maximum of 2 electrons. So in the quantum hotel, the S room, because it has 1 bed, can hold 2 people. The P room has 3 beds, it can hold 6 people. I'll skip D. The F room has 7 beds, it can hold 14 people. So an electron configuration is just a listing of the sublevels and how many electrons they are in. So I think of this for the the quantum hotel as being what the hotel desk clerk is writing down to keep track of who's sleeping where, so that when someone else comes in, he can say, oh, here, I'll give you this room. And he doesn't send them somewhere that's already occupied. So as an example, krypton has 36 electrons. This is its electron configuration. So the first level, there's the S sublevel, and there's 2 electrons in there. The second level, S sublevel, has 2 electrons. The second level, the P sublevel, has 6 electrons. On the third floor of the hotel, the S room has 2 people in it. The P room has 6 people in it. And then that 4S room is less expensive than the 3D room. It's like some Groupon deal, or maybe because it's closer to the elevator. I don't know. Make up your own reason. So the 4S room will fill up first, and then the 3D room will fill up, and then the 4P room will fill up. And I'll show you again on the periodic table how we can see those weird orderings. So that's a lot of, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, lots of numbers and letters. Yes?
Why is there I lost my question.
I imagine that your question is, why is the 4s before the 3d? The 4s is because the 4s orbital is able to penetrate more closely to the nucleus, and so it's lower in energy than the 3D orbitals. So that'll fill first.
So if we add we have the F level in there too, and the F level go, so say we have 3F for like a really big element, where would that go?
So the third level doesn't have any F, but the fourth does. Yeah, and so we'll get to that.
I think
Well, hold on to that confusion, and we'll explain a little more, and maybe it'll clear itself up. So we can look at the periodic table and see that krypton is element number 36, has 36 electrons. If you take the time to add up these superscripts, you'll find out that they add up to 36. Okay, so that's one way you can check an electron configuration to make sure that you at least have the right number of electrons in there. This, of course, can get pretty long and tedious, and so there's a shorthand way. It's called an inner electron configuration, or I call it the noble gas configuration, in which we abbreviate much of this just using the symbol of a noble gas. So looking at the element that comes after krypton, which is rubidium over there, 37 electrons. So this part right here is the same as krypton, right? I didn't mean to do that, I meant to do this. This part in the box is the same as krypton. So instead of writing all of that out, we just write the element symbol for krypton in brackets. And we understand that that is an abbreviation for the electron configuration of krypton, and then 5s1. So you need to be able to do it both ways and to understand what we mean both ways. So we've talked about hydrogen and helium. We'll just go through some of the smaller elements. Here's lithium. Lithium has 3 electrons. I like the to look at the orbital diagrams first. So when I draw orbital diagrams, I'm going to just imagine that I'm drawing the rooms and the beds in the hotel, and I'm just going to draw as many as I need. So here on the first floor, there's an S room, and I can put 2 people in there. On the second floor, there's another S room, and I could put 2 people in there, but I only need to put 1 person in there. So now I've accounted for the 3 electrons in lithium. And then the electron configuration can be read directly from the orbital diagram. Here's 1s, it's got 2 electrons, so 1s2, and the 2s has 1 electron, so 2s1. Add another electron, beryllium has 4. That next electron is going to pair up in the 2s orbital, and now the electron configuration is 1s2, 2s2. For boron, 5 electrons. The 1s room, the 2s room are full. This electron's going to have to go into the next most expensive room, the next higher energy sublevel, which is 2p. And so he's going to occupy one of the beds in there. So then this would be 1s2, 2s2, 2p1. Carbon has 6 electrons. We put another 1 in there. The orbital diagram shows us that these 2 electrons are in separate orbitals within the same sublevel. The electron configuration doesn't specify that, doesn't have that detail. It's 1s2, 2s2, 2p2. Any questions right now? So let's draw an orbital diagram for argon and determine the number of unpaired electrons. Well, how many electrons does argon have? 18. Right, so I'm doing this for argon. It's got 18 electrons. So I'm going to start out by just drawing some beds in my hotel. So on the first floor, I've got the 1S room. On the second floor, I've got an S room. I also have a P room that has 3 beds. They're all in the same room, so I'm going to draw those boxes close together. And then that's the end of the second floor, so up to the third floor. And after the S room, there's another P room. And we could go on, but maybe we don't need to, so let's see if that's far enough. So now I'm going to draw arrows in here and count, right? So 1, 2, 3, 4, 5, 6. He wants his own bed. 7. Now we have to pair up. 8, 9, 10. Oops. 11, 12, 13, 14, 15, 16, 17, 18. 18 electrons. That's the orbital diagram for argon. We could write an electron configuration from that. The 1s has 2 electrons. 2s has 2 electrons. 2p has 6. 3s has 2. 3p has 6. How many unpaired electrons are there in argon? 0. They're all paired up. We can tell that from the orbital diagram. We don't really get that information from the electron configuration.